Hello learners, welcome to NIOS Studio. This program is based on Senior Secondary Chemistry course. I am Dr. Alka Mehrotra. We will be continuing Lesson 7 Solutions. During this part of the program, we will discuss about colligative properties, osmosis and osmotic pressure, abnormal colligative properties, Hoff factor. Colligative properties. So, in this part 3, colligative properties, osmosis and osmotic pressure, abnormal colligative property and Hoff factors. The properties of dilute solutions which depend only on number of particles of solute present in the solution and not on identity are called colligative properties. Now, colligative properties we have in that osmosis and osmotic pressure, elevation of boiling point, depression of freezing point, relative lowering of vapor pressure. Let's revise Raoult's law. To start with relative lowering of vapor pressure. So, if the total vapor pressure of the solution is P, we have done in Raoult's law that PA is equal to P naught A XA, and for the binary mixture XA plus XB is equal to 1. Therefore, XA is equal to 1 minus XB. Now, substituting the value of XA in the equation, we get PA is equal to P naught A 1 minus XB. So, PA upon P naught A is equal to 1. Therefore, P naught A minus PA upon P naught A is equal to XB. This is the Raoult's law. Now, continuing with that, so it will be more clear to you. Now, according to Raoult's law for solutions containing non-volatile solution, that is POA, that is P naught A minus PA upon P naught A is equal to XB. Let's take this as equation 1. Now, also XB is equal to mole fraction like NB upon Na plus NB, where P naught A minus PA represents the lowering of vapor pressure, XB is mole fraction of solute, WA and MA that we will be doing. So, there that will be the masses and molar masses. Now, here in the dilute solution, you know that NB is very less than Na. Therefore, the term NB can be negligible. So, in denominator, if you just remove that thing, so solute is very less. So, there we can say XB is equal to NB upon Na, where WB upon MB is equal to WA upon MA, because we know the mole is, the number of mole is equal to W upon M. Now, WB into MA upon WA into MB. So, therefore, the equation can be written as P naught A minus PA upon P naught A is equal to XB, which is equal to WB into MA upon WA into MB. So, this expression can be used to determine the molecular mass of the solute B. If the relative lowering of vapor pressure of a solution of known concentration and molecular mass solvent are given. Okay. Now, let us do elevation of boiling point. Now, boiling point of a liquid is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. So, vapor pressure of the solvent decreases in the presence of non-volatile solute. This we have discussed in part 2. The boiling point of a solution is always higher than that of boiling point of a pure solvent in which the solution is prepared. So, the elevation of boiling point also depends on the number of solute molecules rather than their nature. Now, let's discuss the difference between these two, elevation of boiling point and depression and freezing point. So, boiling point of a liquid is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. Now, what is freezing point? Freezing point of a substance is the temperature at which the vapor pressure of the substance in its liquid phase is equal to the vapor pressure in the solid phase. Second is, like in elevation of boiling point, the vapor pressure of the pure solvent is always higher than that of the solution. So, the boiling point of the solution is always higher than that of a pure solvent. While in depression and freezing point, the freezing point of the solution is always less than that of the pure solvent. Thus, there is a depression in the freezing point of the solution. This is because the vapor pressure of the solution is always less than that of the pure solvent. If you see the vapor pressure curves of the solvent and solution, you will find that there is an elevation in the boiling point of the solution. Now, you can compare this elevation of the boiling point and the depression and freezing point. The graphs are totally different. Okay, now I will explain it on the board, and it will be, I want you to see it comparatively. So, then it will be more clear to you. Elevation of boiling point. Let delta T be the elevation in boiling point, delta P be the lowering in vapor pressure. Then delta T be, that is directly proportional to delta P, because this lowering in vapor pressure is directly proportional to the elevation and boiling point. So, we can simply write delta Tb is equal to K into Xb. Now, K is a proportionality constant. Let us take this as equation 1. So, Xb is equal to Nb upon Na plus Nb, that we have already done. So, in dilute solution, Nb is very less than Na. It means the quantity of solute is very less. Hence, Nb is negligible in denominator. So, what we can do? Just remove this, because as this Nb is negligible, we can just neglect it in the denominator. So, we get Xb is equal to Nb upon Na. Now, we know that N, this is the number of mole which is equal to the mass upon atomic mass. So, let's put this again formula. W, instead of Nb, we can write Wb upon Mb. Same goes for Na. Wa upon Ma. Now, solve it. Wb upon Mb is multiplied by Ma upon Wa. Right. Now, here this Nb is equal to Ma upon Wa, we can write, because this we are taking as Nb. Okay, now substituting the value of Xb in the equation 1. Now, here we are going to put this Xb value. Xb value we got here, this one. So, if you see here, delta Tb is equal to K. Now, put the value of Xb here, Nb into Ma upon Wa. If the mass of solvent Wa is taken in kilogram, then the term Nb upon Wa is molarity. It means this Nb and Wa is molarity. So, what we get ultimately, that is delta Tb is equal to K. So, we are writing K here, Ma into molarity M, because Nb upon Wa is a molality. So, we are writing here as small m molality. So, this will be equal to Kb upon small m. In the first part, I told you that molality is always defined as small m. So, Kb is called the molar elevation constant for the solvent. Now, Kb may be defined as the elevation and boiling point, when 1 mole of solute is dissolved in 1 kilogram of the solvent. So, Kb is expressed in degree per molality. So, this is elevation of boiling point. Now, let us discuss depression and freezing point. Here, a depression and freezing point, let's take as TF. So, TF be the depression and freezing point. Now, we know that delta TF is directly proportional to XB. So, delta TF is equal to KXB because we have removed this proportionality sign and we have put K. So, K is the proportionality constant. So, XB is equal to NB upon Na plus Nb, that you all know, because it's a mole of solute divided by a mole of solution. So, in the dilute solution, mole of the solute will be very less. So, Nb will be very less as compared to Na. So, hence Nb can be neglected from the denominator, as I told you in the boiling point case. So, Xb is equal to Nb upon Na because Nb is negligible. So, we will not take it, we can neglect this factor. So, now here Nb is equal to Wb upon Ma and Na is equal to Wa upon Ma. Now, we will arrange it, we get this, and we know Wb upon Mb is Nb. So, substitute this by Nb, so you get Nb is into Ma upon Wa. Now, substituting this value, now Xb value we get Nb into Ma upon Wa. Let's put this value in equation 2. So, equation 2 was delta Tf is equal to Kxb. So, delta Tf is equal to K. Now, instead of Xb, we are writing this. So, Nb into Ma upon Wa. If the mass of the solvent Wa is taken in kilogram, then Nb upon Wa becomes molality. So, this is again, this part is molality. So, here delta Tf is equal to Kma into small m, or we can say Kf into m. So, the constant Kf for the solution is called molal depression, constant for the solvent. So, Kf may be defined as a depression in freezing point of a solution when 1 mole of solute is dissolved in 1 kilogram of solvent. The next property, colligative property, this is osmosis and osmotic pressure. If raisins are soaked in water for some time, they swell. This is due to the flow of water into the raisins through its skin, which acts as a semi-permeable membrane, permeable only to solvent molecules. In this case, the solvent flows from the solution of lower concentration to the solution of higher concentration. So, the process continues till the concentrations of the solution on both the side of membrane becomes equal. So, osmosis and osmotic pressure, what exactly is this? This is a definition, like osmosis is the phenomenon of the passage of pure solvent from region of lower concentration of the solution to the region of its higher concentration through the semi-permeable membrane, while osmotic pressure is from excess pressure which must be applied to the solution in order to prevent flow of solvent into the solution through the semi-permeable membrane. Now, so you can see here in the figure, the osmotic pressure may be defined as the excess pressure that must be applied to the solution side to just prevent the passage of pure solvent into it when the two are separated by perfect semi-permeable membrane. You can see the height. So, the pi is there, which is equal to HPG, the solvent and solution, and both are separated by semi-permeable membrane. So, if the two solutions have the same osmotic pressure, they are known as isotonic solutions. The osmotic pressure is a colligative property. It depends on the number of particles of solute present in the solution and not on their nature. This is the property of colligative. At a given temperature T, the osmotic pressure which is denoted by pi, of a dilute solution is experimentally found to be proportional to the concentration of the solution in mole per liter. So, let us do this mathematically. Pi is equal to, that is osmotic pressure is equal to CRT. C here is a concentration. Now, we can write instead of C N upon V. Okay, so pi here is osmotic pressure, V is the volume of a solution, N is the number of mole of solute that is dissolved, R is gas constant and T is absolute temperature. Then we have something reverse osmosis and water purification, which is very common. In our house we have RO system, so this is based on that. Now, as the name suggests, reverse osmosis is just the reverse process of osmosis. Osmosis can occur naturally whenever there is a difference in concentration between the two solutions. But reverse osmosis takes place only when external energy is applied to the more saline solution. Application of larger osmotic pressure to the solution side reverse the direction of osmosis. So, reverse osmosis and water purification, if a pressure higher than the osmotic pressure is applied to the solution side, the direction of flow of solvent can be reversed. As a result, the pure solvent flows out of the solution through the semi-permeable membrane. This process is called reverse osmosis. It is of great practical application as it is used for desalination of seawater to obtain pure water. Now, we have done colligative property. Now, something which is known as abnormal colligative property. So, colligative properties of the solutions depend on only upon the number of solute particles present in the solution and not on their nature. But sometimes while measuring colligative properties, abnormal results are obtained due to the few reasons. So, few reasons of abnormal colligative properties are: if the solution is very concentrated, the particles of the solute start interacting with each other. Therefore, the solution should not be concentrated. Second is, in case of association, two or more solute molecules associate to form a bigger molecule. So, the number of effective molecules in solution therefore decreases. So, consequently, the value of colligative property, relative lowering of vapor pressure, elevation of boiling point, depression, freezing point or osmotic pressure is observed to be less than that calculated on the basis of unassociated molecules. Since the colligative property is inversely proportional to the molar mass, the molar mass of such solutes calculated on the basis of colligative property will be greater than the true molar mass of the solute. Now, the third is, in case of dissociation of the solute in solution, the number of effective solute particles increases. In such cases, the value of observed colligative property will be greater than that calculated on the basis of undissociated solute particles. So, the molar mass of the solute calculated from the measurement of colligative property will be lower than that of the true molar mass of the solute. Hence, the value of molar mass is either lower or higher compared to the expected or normal value and is known as abnormal molar mass. So, in 1880, Hoff introduced factor I that was named as Van 't Hoff factors. So, the Van 't Hoff factor account for the degree of dissociation or association. So, the Van 't Hoff forces I can be defined as the ratio of normal molar mass to the abnormal molar mass. So, mathematically we can say I is equal to observed colligative property, which is the actual one, divided by theoretical colligative property which is expected. So, it means it is equal to the number of molecules actually present divided by number of molecules expected to be present. Now, degree of dissociation and degree of association, what exactly are they? So, degree of association is that may be defined as the fraction of the total number of molecules which associate to form a bigger molecule. For example, benzene, 2 molecules of benzoic acid associate to form a dimer. Like you know, the formula of benzoic acid is C6H5COH. If 2 molecules combine together, associate together, you will get C6H5COOH twice. If X represents the degree of association of benzoic acid and benzene, that is, out of 1 molecule of benzoic acid, X molecules associate to form a dimer. Now, why dimer? Because 2 molecules are combined together or associate together. Then at equilibrium, so the number of moles of unassociated benzoic acid is 1 minus X. Number of moles of associated benzoic acid is X divided by 2. Total number of effective moles of benzoic acid is 1 minus X plus X by 2. So, that is equal to 1 minus X by 2. So, according to the definition, Wonsoff factor is given by I is equal to total number of moles of solute in the solution divided by expected or calculated number of moles of solute, which is equal to 1 minus X by 2 upon 1. Now, degree of dissociation. Degree of dissociation may be defined as the fraction of total number of particles that dissociates, that is break into the simpler ions. Like suppose if you take the example of KCl, potassium chloride in water. So, when KCl is dissolved in water, it dissociates into K ion and Cl ion. So, cation and anions are formed. Let X be the degree of dissociation of KCl. Then at equilibrium, number of moles of undissociated KCl is equal to 1 minus X. So, according to dissociation of KCl shown above, when X mole of KCl dissociates, X mole of K ion and X mole of chloride ions are produced. So, thus the total number of moles in the solution after dissociation will be 1 minus X plus X plus X, which gets 1 plus X. So, ultimately what formula we will get Wonsoff factor is total number of mole of solute in the solution upon expected or calculated number of moles of solute. So, that will be 1 plus X upon 1. Okay. So, here this ends the chapter. Now, let us revise what we have done. Freezing point we have done, which is it's a temperature at which the solid and the liquid forms of the structure substance have the same vapor pressure. Abnormal results are obtained when the solute associates or dissociates in the solution. Wonsoff factor is defined as the ratio of normal molar mass to experimentally determined molar mass. So, here this ends. Thank you.